Dear students, in this section we are going to learn how to calculate the magnetic field due to the large current carrying sheet. Suppose we are having a infinite metal sheet. In this diagram you can observe this is a large sheet having the infinite dimension in the backward direction, left direction, right direction as well as in the front direction. The direction of the current is represented by the cross. That means the direction of the current is away from you, or you can say perpendicular to the screen and away from you, right? For finding the direction of the magnetic field above the sheet, we use the right hand rule. If we stretch our thumb in the direction of the current, the curling of the finger direction represents the direction of the magnetic field. So this thumb stretch in the direction of the current, and we can observe the direction of the magnetic field should be like this, right? This is the direction of the magnetic field. Similarly, below the sheet, we can find the magnetic field direction by using again right hand rule like this. Okay, you can observe here the direction of the magnetic field should be perpendicular to the finger and like this. That means top of the sheet, the direction of the magnetic field from left to right parallel to the surface of the sheet, and also below the sheet it is from right to left again parallel to the sheet. If you want to observe the appropriate direction or exact direction, let us observe the front view of the sheet like this. Okay, you can observe the direction of the magnetic field like this and below like this. This is in the rightward direction, this is in the leftward direction. Now let us move to how to calculate the magnitude of the magnetic field. For this, let us select one illustration for this purpose, right? So let us take the illustration number 1. It says a current I flow in a long straight flat metal strip of width A. There is not infinite. We will generalize this result for infinite also. But in this particular case, this is infinite in the front and backward direction. But in this direction, it is having the finite dimension, and direction of the current you can observe it is toward you, right, away from the screen. And we need to find the magnetic field at point P. P is this point at a distance capital R from the center of the strip, right? That is along its perpendicular bisector. So we need to calculate the magnetic field at this position. Okay, we can consider this metal sheet is made of a number of the wires. We can consider this as this sheet is made of a infinite number of the wire placed side by side. So let us consider one of the small wire, that's the elemental wire like this. Okay, at a distance x from the center of the sheet, and thickness of this elemental wire we can consider as dx. So this will act as a infinite wire, and thickness of this infinite wire is dx. And we know current is distributed over this length, that is A. So we need to find the current density. Current density should be equal to I divided by A, and if we multiply I divided by A by dx, we can find current corresponding to this strip. So let us find the current corresponding to this elemental strip. So let us write di current for this. This is equal to I divided by A multiplied by dx. Okay, now this is acting as a infinite wire, and we know the formula for calculating the magnetic field due to the infinite wire, and we also can get the direction of the magnetic field because of this infinite wire. So let us find first the direction. This distance is x. Let us join this point from this point where we need to calculate the magnetic field. And magnetic field, for finding the direction of the magnetic field, we again use the right hand rule, that is the thumb in the direction of the current and curling of the finger give the direction of the magnetic field. So here we can observe the magnetic field should be perpendicular to this dotted line. This is the direction of the magnetic field. This is dV, right? And distance of this point P from this infinite wire is small r. So here we can write magnetic field due to this elemental wire is mu naught divided by 2 pi di divided by small r, right? This is the formula we need to use, and we can make the component of this. dB. This is the component parallel to the surface of the sheet, and this is the perpendicular to the surface of the sheet. And if we take one more strip at an equal distance, suppose this is the strip, and if we join this strip from this point, the magnetic field dB will be in this direction, right? And if we make the component of the dB, this will be in this and this direction. That means the component of the magnetic field of this strip get cancelled by this component. That means we will have the net magnetic field that is parallel to the surface of this strip. Okay, suppose this is dB cos theta, this is dB sin theta. So we can say dB sin theta will get cancelled by this strip. Okay, let us make the front view of this situation. If we make the front view, we will find the current is toward you. So these are the dots. Point P is at a distance capital R, right? And this strip is here at a distance x, and thickness is dx. Okay, and this is the small r, and direction of the magnetic field is dp, like this, and this is the component parallel to the surface, this is perpendicular to the surface. And suppose this angle is theta, right? So this angle should also be theta. Okay, this is dB cos theta and this is dB sin theta. As we discussed, dB sin theta will get cancelled. Okay, so let us find the value of dV, that's the magnetic field due to this strip. As we discussed, this strip will serve as an infinite wire and it is having current dI. So we can write dB equal to mu naught divided by 2 pi dI divided by small r, right? And we can observe this is a right angle triangle, and we can find the value of small r because this is the known value. So here we can write small r equal to under root of x square plus r square, right? And dI value we have calculated. This is mu naught, this is I divided by a multiplied by dx. So let us substitute this value. Okay, as we discussed, this component dB sin theta will get cancelled. That means net component is equal to dB cos theta. It means the net magnetic field at point P because of this current strip should be integral of dB cos theta. So let us write this as an integral of dB cos theta. Now we need to find this integration, and we know the value of dB, that is mu naught divided by 2 pi I dx divided by a, and this is 2 pi under root x square plus r square. Okay, and cos theta is equal to capital R divided by small r, and small r equal to under root x square plus r square. So let us write this value, that is the integral dB cos theta. Now value of dB and cos theta. Now we can rearrange this equation. We know this mu naught I and r and a also and pi, these are the constant term, and limit of integration should be equal to minus a by 2 plus a by 2 because we are taking distance from middle of the strip. So limit of this is minus a by 2 and this is plus a by 2. So this is the final equation, and we have the standard formula of this type of integral. This is equal to 1 by r tan inverse x divided by r, and limit is minus a by 2 to a by 2, right? Now we can put the limits. This is the final result, right? This is the b equal to, now we can write b equal to mu naught I, this 2 and 2 will get cancelled. So we can write mu naught I divided by pi a tan inverse a divided by 2r, right? Now let us consider the case of the infinite strip, because this strip is infinite from the front and back, but finite in the left and right side. That means if it is infinite strip, that a should be also infinite. That means if we place a tends to infinite in this equation, this will be equal to tan inverse infinite, right? Or you know, tan inverse infinite is nothing but it is pi by 2. So in place of this we can write pi by 2, and pi and pi will get cancelled. So we have the result mu naught I divided by 2a, And we know I divided by A is nothing but current density over this strip or over this side. So we can write I divided by A by, we can represent I divided by A, that is the current density, by a different term, that say J. So we can write mu naught J divided by 2. So magnetic field at top of this strip is mu naught J divided by 2. You can observe this expression is independent of the distance when the strip is infinite. Similar case we can say, if we want to find the magnitude of the magnetic field below this strip, this will also have the same value, mu naught J divided by 2. Now let us move to next illustration. In this illustration, it is given a current I flow in a long straight wire with cross section area having a form of thin half ring of radius capital R, as shown in the figure. You can observe here, this is the cross sectional area of a long wire. The cross section is of the shape of semicircle of radius capital R. And here we need to find the induction of the magnetic field at O. O point is point lying on the axis of this semicircle. You can observe here the axis of this semicircle should pass through O and perpendicular to the screen, and we need to find magnetic field at this point. Okay, so let us make the complete view of this structure. This is the complete view, three-dimensional view you can observe. Let us assume the direction of the current in this wire. Let us assume the current is away from you. So this is the direction of the current, right? You can observe this current will distribute uniformly on this section. So here we can assume this wire or this cross section is made of a number of the wires placed side by side in the form of the semicircle, right? You can assume these red color lines as a wires placed side by side. And we can find the current density also. Suppose current is I, that means current density should be equal to I divided by pi r, because length of this section is pi r. Okay. Now let us make the position of point under consideration where we need to find the magnetic field. This is the axis, and this point O where we need to find the magnetic field. Now let us make the cross sectional view of this wire. This is the cross section view of the wire. And as we discussed, we can assume this wire is made of a number of the elemental wire. So let us consider one elemental wire in this section, this one, and this is on the cross section view, right? The angular position of this wire with respect to O or with respect to this dotted line is theta, and this is the direction of the current away from you. So this is the angular position theta, right? The angular width of the wire will be calculated if we join this point to this point. This is the theta. This is the angular width of this wire. And now length of this wire can be calculated by using this arc length equal to angle multiplied by radius, r d theta. Now we can consider this is an infinite wire, and because of infinite wire, if you are interested to find the direction of the magnetic field, so direction of the magnetic field can be calculated by using the right hand rule. So if we place the thumb in the sense of the current, curling of the right hand will give the direction of the magnetic field. Say this is dB. Okay, this is the direction of the magnetic field. Now let us consider one more elemental wire at the symmetrical position. That means this angle is again theta. The current direction is again cross, right? This is the position of the second elemental wire. This elemental wire also create the magnetic field at this position. Let us assume the magnetic field from this wire, magnitude of magnetic field created by this wire is again dB. So using the right hand rule, we can find the magnetic field direction like this, right? Magnitude of this and this will be the same. That means the vertical component, that is the y component of dV, will get cancelled. We will have only the horizontal component. Similarly, if we add all the elements, vertical component, that is the vertical upward and downward component, will get cancelled. We will have the net magnetic field in this direction. Okay, this is the direction of the net magnetic field. Now let us calculate the value of current in this section, dI. As we discussed, current is uniformly distributed over the cross section. So current flowing through this section should be equal to I divided by pi r, that is the current density, multiplied by length of this section, that is RT theta. So current in this elemental wire is equal to di equal to I divided by pi r multiplied by RT theta. R will get cancelled. That means I d theta divided by pi. This is di value. Okay. Now let us calculate the magnetic field dV because of this. Now we know this is acting as an infinite wire. So let us find the magnetic field because of this, right? We know the formula of the magnetic field due to the infinite wire. This is equal to mu naught multiplied by current I divided by 2 pi multiplied by distance from point under consideration to the wire. So here the current is di and distance of point under consideration to the wire is capital R. So we can write mu naught di divided by 2 pi r. Okay. Now we can substitute the value of di. This is I d theta divided by pi. So this is the dV value, right? Now let us find the net magnetic field at this position, that is dB net. We can observe here this radial line, dotted radial line, is making theta degree with the vertical direction, and dB is perpendicular to this radial line. That means the dB should make angle theta with the horizontal direction. That means this angle should be equal to theta. That means the effective component of the magnetic field in this direction should be equal to dB cos theta. That means the net magnetic field at O should be equal to integration of dB cos theta. The limit should be equal to from minus pi by 2 to plus pi by 2, right? Now let us integrate this value. We know the value of dV, right? So let us write this expression. Okay, the value of dV we have calculated, this one. So let us substitute the value. Now we can place the constant term mu naught I divided by 2 pi square r outside the integral, right? Now we can make the integral minus pi by 2 to plus pi by 2 as 2 multiplied by 0 to pi by 2. So this is mu naught I divided by 2 pi square r multiplied by 2, 0 to pi by 2 cos theta, and integration of the cos theta equal to the sin theta. Now we can put the limit, and after placing the limit, this is equal to mu naught I divided by pi square r, and this is sin pi by 2 minus sin 0. So this is 1 minus 0. After calculating, we will get the value mu naught I divided by pi square r. So this is the magnetic field because of this metal strip, right? Now let us move to next illustration. In this illustration, we are given conductor of length capital L has shape of the semi-cylinder of radius capital R. Capital R is much smaller than capital L. You know the cross section of the semi-cylindrical should be semicircular, and the radius of the semicircular section is given as capital R, and capital R, that is the radius, is much smaller than length of the conductor. Cross section of the conductor is shown in the figure. You can follow this figure. This of course is a semicircular of radius capital R. The thickness of the conductor is small t. This is the thickness, small t, and this thickness is again much smaller than radius of the cross section, and the conductivity of its material varies with the angle theta. This is the variation of conductivity, that is sigma equal to sigma naught cos theta. That is, theta is measured from this vertical line, and conductivity varies with this relation. That is, conductivity in all section is not constant. That is, the resistivity of the section, all section is not constant. It is changing from position to position, okay, according to this law. This law is for conductivity. If a battery of EMF capital V and negligible internal resistance is connected across the end faces, right? Now we have connected a battery of negligible internal resistance, that is ideal battery, across this conducting wire of length L, right? And we know the conductivity is changing from position to position. That means the resistivity is also changing from position to position, but we have applied potential difference. That means the current will start flowing from one end to other end. and because of variation of the resistivity, resistance of each and every section will keep on changing. That means different current will flow from different section. Okay, and we can say because of the symmetry, the current flowing at this position, say this position is a theta position here, and current flowing the same theta position at symmetrical position should be the same, right? And we need to calculate here the magnetic induction at the midpoint capital O of the axis of the semi-cylinder. Now we need to calculate the magnetic field or magnetic induction at axial point, certain axial point on the semi-cylinder, right? So let us make the diagram of this cross section in complete form. This is the diagram, right? You can observe here we have connected a battery across this wire. So let us consider current is entering through this section and coming out from this section. We can consider this wire, this cross-sectional wire, this cylindrical, semi-cylindrical wire is made of a number of the wires, straight wire, placed side by side, right? You can consider these red lines or red arrows as a straight wire, long straight wires. We are considering these wires as a long wire because this length of the cylinder is much greater than the radius of the cross section. So here we can consider this length as a infinite length in comparison to the radius, because this value capital S is very large. But we cannot consider all current which is represented by arrow as same, because resistance at each and every section is not constant. So we have considered current is away from you, right? That is perpendicular to the plane of the screen and going away from you. And the point under consideration where you need to find the magnetic field should be here, somewhere here at the middle point of this conducting wire. Conducting wire is having length L. So at the middle point on the axis, this is point O, right? Now let us consider one elemental wire somewhere here. And now let us show this conducting wire or elemental wire, or you can say elemental resistance in the cross section of this, right? So let us assign the position here. And this is a current going away from you, so here should be cross. Angular position of this elemental wire is theta, and theta is measured with respect to the vertical line. So let us join O with this wire, and this angle is theta. Let angular width of this wire, elemental wire, is d theta. That means the length of this section, length of this elemental section should be equal to r is the radius, multiplied by d theta. So this is the length. Okay. Now the magnetic field, because of this wire, we can use the right hand rule. While using the right hand rule, what we do, we stretch the right hand thumb in the direction of the current and curl the finger. That curling finger direction give the direction of the magnetic field. So this is the dB vector, right? Because of this. Now let us consider one more element at the symmetrical position, that is the left side here, and current is here again cross, because current is moving away from you. This is also theta position. So the magnetic field because of this elemental wire should be calculated by using the right hand rule again. So using the right hand rule, we can find the direction of the magnetic field like this, right? This is the wire. So direction of the magnetic field should be like this. Okay. The current value in this elemental wire and current value in this elemental wire will be same, because the conductivity is same. Conductivity is function of theta, and we have considered the symmetrical wires. So conductivity is same, that is resistivity is same. Resistivity same means resistance is same, potential difference is same. That means current in flowing through this section and this section should be the same. That means dB and dB, that should be the same. That means the vertical component of dB and vertical component of this dB will get cancelled. We will have the net component in the rightward direction, horizontal direction. and similar statement true for all the sections on this cross section. That means the net magnetic field because of this cross section or because of this wire should be in the rightward direction, dB. Okay. So this is the net magnetic field. Now we know the electric conductivity of the material is sigma equal to sigma naught cos theta, right? And we know the resistance of each element wire can be given by this relation R dash equal to L divided by sigma A. You might have learned the relation R equal to rho L divided by A. Rho is the resistivity, and we know conductivity is 1 divided by resistivity. That's why we have written L divided by sigma A. So this resistance should be equal to L divided by this sigma value, sigma naught cos theta, and cross section of area of this should be equal to, because T is the thickness and length of this section is R theta. That means the area of cross section of this wire should be equal to T multiplied by R d theta. So on rearranging the term, we can write like this. So this is the resistance of this section. We have applied the potential difference V across this wire. So we can write current in this section, say call this current as Di. So we can write Di equal to potential difference divided by resistance. So let us write the expression for the current Di. Di is the current in this section and this section also. So V divided by resistance, and V is given to you, and resistance we have written like this. So this is the current in this section. Okay. Now this wire and this wire, or you can say this wire and this wire, both are long wire. That means we can apply the formula of the infinite wire, right? And we know the formula for the infinite wire or long wire as mu naught I divided by 2 pi R. R is the distance, right? So we can write here the relation. Now we can say this wire or any of the elemental wire can be considered as a infinite wire for calculating magnetic field at point O. Why? Because radius of cross section of this wire is much smaller than the length of the wire. That means we can use the formula for the magnetic field due to the infinite wire. Okay. We have current value in function of theta. So let us consider this element and calculate the value of dB because of this element, because we are considering this as an infinite wire. So magnetic field because of this element at O should be written as mu naught I. In place of I, we should write Di. So mu naught Di divided by 2 pi, distance is capital R, right? So this expression can be used. Now we have value of Di equal to this much. So let us substitute this value. This is the magnetic field at this position O because of this wire or this wire. Okay. And here we can observe capital R and capital R will get cancelled. So we got the value of dV. As we discussed, this effective component of the magnetic field for calculating magnetic field at point O is horizontal, right? Because vertical component of dV from this and from this will get cancelled. We will have the horizontal component. So let us write expression for calculating the net dV, and we know this line, dotted line, is making theta with the vertical. That means any line which is perpendicular to this dotted line will make angle theta with the horizontal. That means this angle should be theta. So let us write this angle is theta. That means component of the magnetic field dV in the horizontal direction is dB cos theta. That means we need to make the integral of dB cos theta, and limit of integration should be equal to minus pi by 2 to plus pi by 2. So let us write B net equal to limits minus pi by 2 plus pi by 2 integral dB cos theta. So let us write this expression to the next page, right? This is the dB cos theta integral from minus pi by 2 plus pi by 2, right? Now let us rearrange this term. Let us substitute the value of dB. dB is this much. We can cancel out capital R. So we can write this expression. Now we can put the constant term, that is mu naught sigma naught v t 2 pi L outside the integral, and this integration is from minus pi by 2 plus pi by 2. So here we can write twice multiplied by integration limit 0 to pi by 2. So let us write this expression. Now we have left with the integral this one, that is 0 to pi by 2 cos square d theta. So let us integrate this relation. Let us write this relation here. Okay. Now we can write this cos square theta is 1 by 2 cos 2 theta plus 1 and d theta integral. Okay. Now we can simply integrate this relation. The integration of cos 2 theta is equal to sin 2 theta divided by 2, and integration of 1, that is d theta, is theta. So this is the relation, and limit is 0 to pi by 2. Now we can substitute the limit, right? 0 to pi by 2, if we substitute 0 in this limit, this will be 0, and here 1 by 2 is common. So this is the, after putting the limits. So final result on calculation is mu naught sigma naught capital Vt divided by 4L. So this is the magnetic field due to this semi-cylindrical wire at the axial position, that is at O, and we can observe this magnetic field is in the rightward direction, that is in the horizontal direction.